Previously, we analogized the basic properties of equations and studied the basic properties, proofs, and applications of inequalities. Today, we will learn a specific inequality, the basic inequality. We know that multiplication formulas play an important role in algebraic operations, but are there also some inequalities that play a similar important role in solving inequality problems as multiplication formulas? Next, we will study this issue. In the previous study, we obtained a class of important inequalities using the perfect square formula, NEA, B belongs to R. The square of A plus the square of B is greater than or equal to 2ab, and the equal sign holds only when A equals B. So please observe this inequality, where the left side is the sum of the squares of two numbers, and the right side is twice the product of these two numbers. We know that the square structure has a higher requirement for this, so can we think about using a number instead of this square structure? For example, we can use it to replace the square of A and B to replace the square of B. Of course, we require A and B to be non-negative, and because if A and B are 0, this inequality is not very meaningful to study. Therefore, we require both A and B to be greater than 0. So for this inequality, the right side was originally the product of A and B. Since we replaced the square of A with A, what should we use to replace the original A? So here specifically, we will use root A and root B to replace A and B in our previous equation, respectively. Please think about it. What kind of equation can you get? Let's solve it together. By replacing the A and B with the roots A and B in our original A plus B square greater than or equal to 2ab, we can obtain the product of the square of root A and the square of root B, which is greater than or equal to twice the number of roots A multiplied by B. That is, A multiplied by B under the root of A plus B is greater than or equal to twice the number of roots. By adjusting this inequality, we can obtain that the product of A and B under the root is less than or equal to half of A plus B. At this point, we arrive at a conclusion: for any A greater than 0, B greater than 0, ab under the root sign is less than or equal to half of A plus B. If and only if A and B are equal, the equal sign holds. We usually refer to this inequality as the fundamental inequality, where half of A plus B is called the arithmetic mean of positive numbers A and B, and ab under the root is called the geometric mean of positive numbers A and B. So from the basic inequality, we can see that the root ab is less than or equal to half A plus B, indicating that the arithmetic mean of two positive numbers should not be less than their geometric mean. Okay, can you use the properties of the inequalities we learned earlier to prove the fundamental inequalities? Here, of course, everyone can contact the real number ratio size we learned earlier and use the difference comparison method to prove it. So today, I'm going to introduce a new method called analytical method. Analytical method is a commonly used proof method in mathematics. It is a method of causal reasoning, which starts from the conclusion to be proved, gradually seeks sufficient conditions for it to hold, and finally reduces the conclusion to a clear condition for determining its validity. This condition can be a known condition or a theorem, definition, axiom, etc., that we have learned before. So the basic inequality we need to prove is, for A greater than 0 and B greater than 0, to prove that ab under the root sign is less than or equal to half of A plus B. We only need to prove that ab under the double root sign is less than or equal to A plus B. To prove that ab under the double root sign is less than or equal to A plus B, we only need to prove that ab under the double root sign minus A minus B is less than or equal to 0. To prove that ab minus A minus B under the double root sign is less than or equal to 0, it is necessary to prove that the square of the negative root sign A minus the root sign B is less than or equal to 0. To prove that the square of the negative root A minus the root B is less than or equal to 0, as long as the square of the root A minus the square of the root B is greater than or equal to 0. We can see that the equation root A minus root B, square of parentheses greater than or equal to 0 is clearly true, and the equal sign holds only when A equals B. So at this point, we just need to reverse the above process and directly derive the basic inequality. After going through the derivation process above, you can see that we start from the problem we want to prove and gradually search for sufficient conditions for each proposition to hold, until finally reaching the formula that the square of the root A minus the root B is greater than or equal to 0, which obviously holds. Through the previous proof process, we can see that we have gone through the process of starting from the problem we want to prove, gradually seeking sufficient conditions for the mission question to hold, and finally coming down to determining a formula that is clearly valid. That is, until the square of root A minus root B is greater than or equal to 0. This is the analysis method we will introduce to you today. So please think about it. What is the basis for each step of our reasoning in the proof process above? For example, we derive inequality 1 from inequality 2, which means that ab under the double root sign is less than or equal to half of a plus b. According to the properties of our inequality, multiplying a positive number on both sides of the inequality yields an inequality that is in the same direction as the original inequality. Based on the knowledge of necessary and sufficient conditions learned earlier, we can know that inequality 2 should be a sufficient condition for the validity of equation 1. So, from inequality 3, we can deduce inequality 2, which means that ab is less than or equal to a plus b under the double root sign, and ab is less than or equal to a plus b. Based on the properties of the inequality, we add positive numbers a plus b on both sides of the inequality, and the resulting inequality should be in the same direction as the original inequality. Here, we can also know from the previous knowledge that inequality 3 is a sufficient condition for equation 2 to hold. Derive inequality 3 from inequality 4, that is, subtract the root b from the negative root a, and the square of the bracket is less than or equal to 0. Derive ab minus a minus b under double the root, which is less than or equal to 0. Here, we use the complete square formula to simplify the calculation, and we can also conclude that inequality 4 is a sufficient condition for inequality 3 to hold. Derive inequality 4 from inequality 5, which means that subtracting the square of root b from root a is greater than or equal to 0, and the negative square of root a minus the square of root b is less than or equal to 0. Here, based on the properties of the inequality, we multiply both sides of the inequality by a negative 1, and the resulting inequality should be the opposite of the original inequality. Based on our previous knowledge of necessary and sufficient conditions, we can also know that inequality 5 should be a sufficient condition for inequality 4 to hold. Obviously, inequality 5 holds, and the equal sign in inequality 5 can be obtained only when a equals b. So, after the above analysis, can you summarize the proof format of our analytical method? We know that because the analytical method starts from the proven conclusion and gradually seeks sufficient conditions to make it valid, there must be corresponding textual explanations in the writing process of the analytical method. Generally, each step of reasoning needs to use the format of what needs to be proven, as long as what needs to be proven. Therefore, when a clear condition is derived, it is pointed out that what obviously holds. After the algebraic explanation of the basic inequalities mentioned earlier, can you imagine that from a geometric perspective, basic inequalities also have a background to correspond to them? Let's explore together below. Please take a look at the picture on my blackboard. In the circle, A and B are the diameters of the circle. Point C is a point above the diameter AB, the length of AC is A, and the length of BC is B. Then, let's take a line segment D perpendicular to AB and connect AD and BD. Can you find which line segment corresponds to half a plus B and AB under the root sign in this picture? Can you also derive a geometric explanation for our basic inequality from this graph? Let's take a look together below. We can observe from this graph that since AB is the diameter of a circle, AC has a length of A, and BC has a length of B. The length of AB is a plus B. Therefore, half of a plus b should correspond to the radius of our circle. So who does AB correspond to under the root sign? So we need to think which line segment in the graph could possibly be composed of the product of A and B. It is relatively easy for us to think of proving the similarity between triangle ACT and triangle DC here. By comparing the corresponding sides of similar triangles, we can obtain that the square of CD is equal to a multiplied by B. Therefore, the square of CD is equal to a multiplied by b, which means that CD is equal to AB below the root. Here, we find that half of a plus b should correspond to the radius of our circle, and AB below the root corresponds to the length of the chord CD in our circle. So based on CD being less than or equal to the radius of the circle, we can conclude that AB under the root sign is less than or equal to half of a plus b. Of course, when point C coincides with the center of the circle, that is, when CD is equal to the radius, we can say that the equal sign above holds. Alright, in the diagram just now, starting from the conditions and basic inequalities, we found that the radius of a circle is half a plus b, and CD is equal to AB under the root sign. Therefore, the basic inequality we learned can be explained using the phrase the diameter is not less than any string in the circle. If and only if our string passes through the center of the circle, the two are equal. We can consider this as the geometric explanation of the basic inequality. Previously, we learned about the definition of basic inequalities and used analytical methods and the basic properties of inequalities to prove them. We also learned how to provide geometric explanations of basic inequalities in graphs. Now, let's take a look at how to solve the problem of finding the maximum value of our simple algebraic equations using basic inequalities. Let's take a look at example 1 together. Given that x is greater than 0, find the minimum value of x plus 1/10 of x. Please observe the structure we require for x plus 1/10 of x, and we find that the product of these two positive numbers gives 1. Therefore, based on the basic inequality we have learned before, we can use the relationship between the arithmetic mean of positive numbers x and 1/10 of x and the geometric mean to obtain that the minimum value of x plus 1/10 of x is 2. The following is the process of our solution. Since x is greater than 0, according to the fundamental inequality, x plus 1/10 of x should be greater than or equal to twice the root of x multiplied by 1/10 of x, which is equal to 2. If and only if x is equal to 1 part of x, that is, x squared is equal to 1, that is, x is equal to 1, the equal sign holds. So, the minimum value of x plus 1/10 of x should be 2. So here, I want to ask everyone, in the process of writing, is it necessary to write if and only if x equals 1/10 of x, that is, x equals 1 moment, the equal sign holds? We say it must be clearly stated, because only when x equals 1, our algebraic formula x plus 1/10 of x can obtain the minimum value of 2. So please think again, if I have a y0 that is less than 2, can we say that x plus 1/10 of x is greater than or equal to y0? Can you say that y0 is the minimum value of x plus 1/10 of x? So we know that if y0 is less than 2, it does hold that x plus x by 1 is greater than or equal to y0, but we cannot find an x0 that makes x0 plus x by 1 equal to y0. That is to say, you cannot find an x0 that can be substituted into x plus x by 1, so that it takes your y0. Therefore, when our y0 is less than 2, it cannot be said to be the minimum value of x plus x by 1. That is to say, only when x is equal to 1, our x plus x by 1 equals 2, and this 2 is the minimum value of x plus x by 1. Through the study of example 1, we know that if there are two positive numbers and their product is constant, we can find the minimum value of their sum. Now let's take a look at example 2. Given that x and y are both positive numbers, we can prove the first question. If x multiplied by y equals the constant value p, then when x is equal to y, the minimum value of x plus y is twice the root p. And the second question is, if x plus y equals the constant value s, then when x is equal to y, the product x multiplied by y has a maximum value of 1/4 of s squared. Let's first take a look at the first question. If the product of two positive numbers x and y is equal to p, then when x is equal to y, the minimum value of x plus y is twice the root p. Here, because x and y are both positive numbers, using the basic inequality we have learned before, we can know that half of x plus y is greater than or equal to the root of x multiplied by y. Also, because x multiplied by y equals p, we can obtain half of x plus y is greater than or equal to the root p. Only when x is equal to y, the equal sign in this inequality holds, that is, when x is equal to y, our minimum value of x plus y is twice the root p. Let's take a look at the second question again. If the sum of two positive numbers x and y is equal to a constant value s, then when x is equal to y, their product has a maximum value of 1/4 of the square of s. According to the basic inequality we learned earlier, when the sum of these two positive numbers is equal to a constant value, we know that the product of x and y under the root sign should be less than or equal to half of x plus y, because x plus y equals the constant value s. Therefore, we can write that the root sign xy is less than or equal to half s. Thus, we obtain the square of x multiplied by y less than or equal to 3/4 of s. Therefore, if and only if x equals y, an equal sign is taken above. After studying example 2, we can see that if we are given two positive numbers x and y, and the product of these two positive numbers is a constant value, we can find the minimum value of the sum of these two numbers. When these two numbers are equal, we can take an equal sign. If the sum of two numbers is equal to a constant value, we can find the maximum value of the product of these two numbers, which is also the maximum value obtained when these two numbers are equal. Okay, so after our lesson, we need everyone to get 3 points First, we need to know that the basic inequality is that the arithmetic mean of two positive numbers is not less than their geometric mean. In our mathematical symbol language, for any a greater than 0 and b greater than 0, there is a root sign where ab is less than or equal to half of a plus b. If and only if a is equal to b, the equal sign holds. Secondly, we also learned how to use analytical methods to prove the basic inequalities based on the properties of the inequalities we learned earlier. We also used some known size relationships of line segments in a circle to remember the geometric characteristics of the basic inequalities. Finally, when using fundamental inequalities to find the maximum value of an algebraic formula, we first need to clarify whether the formula can be transformed into the sum or product of two positive numbers, whether their sum or product is a constant value, and whether the equal sign in the inequality can be obtained. We need to achieve first, positive, second, definite, phases, so that we can use fundamental inequalities to solve the problem of the maximum value of an algebraic formula.